my fellow colleagues, Dr. Raju Kumar Pandita, Assistant Professor, Department of Physics, Dr. Kudsiya Gani, Assistant Professor, Department of Physics. I welcome you, sir, in this webinar. Now, I will give the brief introduction of our esteemed guest. He is Associate Professor, Department of Physics, University of Kashmir, Srinagar. He has done BSc Honors in Physics from Aligarh Muslim University, MSc Physics again from the same university, PhD from Aligarh Muslim University on nuclear collisions at relativistic energies. He has done his postdoctoral fellow at Saha Institute of Nuclear Physics, Kolkata. His research interests are relativistic heavy ion collisions and neutrino physics. His published work includes several papers on various phenomena occurring during the collisions of heavy nuclei at high energies. Dr. Wasim Bari has supervised students for PhD thesis on neutrino physics, heavy ion physics, detector physics, simulation tools for nuclear physics. Also, our assistant professor, she is the student of Dr. Wasim Bari. Her name is Dr. Kudsiya Gani. His other fields of interest are study of seismic precursors. He has completed several projects funded by UGC as well as DST, Government of India. He is presently working on India-based neutrino observatory project by DST, Government of India. His collaboration is with CERN, Geneva, ITFR, Mumbai, SINP, Kolkata, IIT, Chennai, IUAC, New Delhi. He has previously worked at European Center for Numeral Research, Geneva for Large Hadron Collider experiments. His special interests are in the study of philosophy of physics, physics education, and the relation between physics and society. He has delivered several talks on these topics at various platforms. Now, I request Dr. Wasim Bari to start his deliberations on the topic pleasure in science. Over to you, Professor Wasim, Dr. Wasim Bari.
Assalamu alaikum warahmatullah. Honorable Principal Ma'am and respected Head Department of Physics, Government College of Women, other colleagues and participants to this webinar. Assalamu alaikum warahmatullahi wabarakatuh and good afternoon. Before I start, actually, I would like to put on record my thanks to the principal and the respected head of the department, so that for having me here and for giving me this opportunity. Today, what I will be actually, so can I share the screen now?
Yes, sir.
Okay. Okay. So we shall right away start our this talk. I suppose the screen is there now?
It's visible, sir.
Okay, fine. Great. So my just a brief introduction to this talk. I have designed it for the undergrad friends who may be thinking of taking science or in particular physics as a career. Okay. And plus, I would like to admit that this is not a hardcore physics talk. Okay, this is for general people. Maybe for our students who are doing physics right now, first part of it may look like a little bit trivial, but that is the basis for our later part of this talk. So I am unconventionally starting this talk with a question that what makes us do science? Okay. So it has been long, but I will be talking about some historical facts about human being doing science. Okay, so it's well-known fact now that humans are innately actually curious creatures. We have a lot of curiosity which leads us to doing things in our lives, and science is one of the most significant things we do out of the curiosity. So we have Einstein's very important quote here that I am neither clever nor especially gifted. I'm only very, very curious. And that curiosity is which actually has led people to do science in a serious and a more significant way. We have examples in our lives where that how this curiosity has actually led us to the modern day world. Okay, the human being since the beginning has been curious. Okay, one of the oldest actually what we say inventions, which is the wheel, and which has revolutionized our understanding of everything. Wheel is considered till date. Wheel is considered to be the most revolutionary invention in the human world. This could not have happened randomly or empirically, that wheel was actually invented. But this is a human invention. There's no indication anywhere that wheel was actually a natural thing. It was an invention. And that invention has been because human beings might have been curious about knowing how we make less efforts and how we can do the things better. We are all aware of the curiosity of Newton's this story of the apple, that it was the whole thing about gravity came out because man was curious about that, those falling things. Okay, then there are a lot of stories about this, like first antibiotic. I have shown a picture here. Okay, how ampicillin was actually this penicillin, this injection was actually, this antibiotic was actually discovered. There is a big story from its who discovered this. Then all the things we know right now, we are curious about knowing what's happening on another planets. That has given the world a new job of exploring the world on the other planets. Man actually landed on moon because of curiosity, and we actually study the innermost parts of atom out of curiosity, because we wish to know that what is inside, and we are curious to know what happens, what are the phenomena happening there. Just a mention of something. This is not a physics slide. Okay, our friends from psychology will know it better. That this fellow actually was so curious that he wrote a book on the science of asking why. So, okay. So Mario Livio. So he says that there are several kinds or flavors of curiosity, which are driven by many different things. But the science in particular is driven by, mostly the literature says that there are two types of curiosities. One is perceptual and another is epistemic curiosity, which actually the first one deals with explaining or trying to understand something which actually is a surprise or a puzzle to us. The other is actually, of course, human being is naturally trying to gain knowledge and excel in its fields, and that's why that epistemic curiosity is there. So with these introductory remarks about the human being most curious actually creature the nature has created. Okay, so we have developed, we have excelled and evolved in our understanding about the science. So what is my talk today? So today what I would be talking about is trying to answer the questions of these two eternal questions, which have been asked by philosophers as well as scientists and sociologists, and everybody is asking these questions, that what is the world made up of, and what holds it in together in the present way which we know. Now there are different views, and but all those views, actually the beginning is the same, and it is not actually science from where it has started. It has started from the philosophy. So like, okay, let us leave this one. Let us go. Let us go to this. There are some historical facts, some philosophical facts, which I would like to put to our friends first. Then we can go to the science of it. Now, this whole phenomenon of understanding the basic constituents of matter has started from philosophers. Empedocles was one of the first ones who actually classified these constituents in earth, air, fire, and water. So he said he was of the opinion that this whole world is made up of these four constituents, and he had a philosophical understanding of this, that this is because these four things actually feel to the human being differently. So this is this is feeling of being dry, cold, hot, and wet. In addition to these philosophical things, there are many theological actually thoughts which have evolved from time to time, like this earth, water, fire thing was also is being observed that in earlier this mm, Chinese literature, you find that this kind of objects are considered to be the ultimate constituents, like earth, wood, metal, fire, and water. And if we see at the Indian mythology, then there are also certain things which actually point towards that there is space, there is air, fire, water, and earth, which actually make this whole world. But these are all things which have evolved. Like somebody called Thales was one more thing who actually considered only water to be the basic constituent. Then another one considered only air to be the basic constituent. And this fellow considered that there is only fire which makes this whole world. But the thing which carried on was actually Empedocles' thinking that we have these four constituents: earth, air, fire, and water, which make this world. Empedocles has one more. This is just a passing remark. So he was a philosopher, and he actually, in that, when conservation of energy or conservation of mass energy was not known really, but then he had said that this is everything is there, but it changes from one thing to another. So this is just that people had actually thought about these things earlier also. This is not my thing today. I'm doing. So I'm talking about here that how this our understanding of the knowing the ultimate constituent or the fundamental thing which makes our universe has evolved from philosophy to science. So okay, so the ancient philosophers who one of the first who actually put forward the idea of this indivisible atom was actually Democrats. So his proposal was actually very simple, that he said that if we actually keep on this breaking this matter actually from one to half, then 1/4, then 1/8, and this we have to have actually a limit where one should stop, where beyond which we cannot actually uh, divide this matter. So he said that there should be something which is indivisible. In Greek, that was actually atomos, and which later came to be known as the atom. So this was very this was in this era, in Democratic era. He said like this. But then there was a tragedy that this human actually civilizations were more affected or more influenced by the philosophers, those philosophers actually who had a lot of influence on the Roman Catholic here on this church, who would actually rule the human civilization then. So there were two people actually, Aristotle and Plato, who supported the idea of this earth, fire, water, and the component. Okay, so So what happened is that the atomos concept was actually borrowed for around 2000 years actually, before actually people came back to the idea of this indivisible atom. But this is all this is the tragic thing which happened in our understanding of the basic constants of matter, that this people who had a lot of hold on the theological things and the civilizations at that time. So this atom, this we could not actually go beyond this for nearly 2000 years, until actually uh, in 1800s actually Dalton, who was doing the chemistry type of experiments, trying to find out the reactions, how different substances react. So he actually was, after Democritus and leaving the era of Plato and this, he was the first who scientifically actually proposed the idea of having some invisible constituents, sorry, indivisible constituents of this matter, which are atoms. So at that time, so we thought about is the this atom. So our understanding at that time was that this atom is now the fundamental thing, until this Thomson came and he could actually see that this atom is not something which is indivisible or indestructible, but it is having certain negative charges inside, and then there is a positive charge which is spread over the whole space of it. So those negative charges were he called as the electron. So that is how electron was actually born. Thomson, our students know that he put this very famous plum pudding model. So these are the electrons, and the whole cake is actually the positive charge deposition. So it was like this. But then his proposal of electron and his finding of electron actually, this actually was in controversy with the atom being a fundamental thing. So atom did not remain fundamental after actually Thomson gave the model. So right now, if we are using atom as fundamental, it is actually a misnomer. So atom is not fundamental. Now what happened after this? I will go fast in these slides because the second part is more important. So after that came Rutherford, who said that okay, there are this atom is not fundamental, right? But this positive charge is not spread over the whole volume. Rather, it is something which is actually concentrated at the center of this atom. So he discovered actually the neutron, this nucleus. And his idea was that since atom is a neutral thing, this has to be a positive center. Okay, and on the basis of those scattering patterns, it was his theory said that there should be a concentrated central part of it, and then space around it contains the electrons. so So at that time, then we thought about that nucleus is now fundamental. Atom is not fundamental, but then there is electrons, and which is nucleus is a fundamental. But this idea also did not last too long, because we had many other things coming in, like we had atom like this, which is called the planetary model. But after that, Bohr came with an idea that this nature would actually like to have these things in order. Nature does not like the disorder like this. So he gave this model of these electrons being in certain specific orbits, and so we have this central nucleus, and we have electrons in the orbits. Now, in 1932, this nucleus was seen to be having another constituent within it, which is the sibling of the proton, that is a neutron, which is a neutral kind of proton, no charge, but similar with proton. So we had, with this, all this background, we had this atom like this, where we have protons and neutrons at the center, and the electrons going around the orbits. So we considered that electrons, protons, and neutrons are the fundamental particles, which again we will deny after certain time. So we knew the electron, this atom like this, and most of this is an empty space. Like you will see that 99 point this percent, it is volume is empty space. The mass is concentrated at the center. If we compare, it is something like this. So 99.97% is the nucleus. Only 0.03% is the rest of the space, but the space, that is 99%. So nucleus is only 1% volume wise, but 99.97% its mass wise. So that is how what was one stage of our understanding of the basic constituents of matter, because there were limitations. Now the point is that this physicists are actually considered to be reductionists, so they would actually try to find out, and they are curious people also. So reductionist means they would try to find out in the smallest thing and try to explain the largest scenario of the things. So with the advent of actually availability of so now our science begins actually, which is the essence of this talk, is that how could we, if we consider protons and neutrons, so we could see inside an atom. Rutherford could see inside an atom, so he could find a nucleus and electrons. But then if you have to see inside the nucleus, so you would have more energy. It's like you are if you have to cross a wooden wall, and if you have to cross a for students I'm saying, if you have to actually cross a wooden wall, or you have to drill actually through a wooden wall, and you have to drill through a concrete wall. So for doing it through concrete wall, you will actually have to do a more energetic thing. So that is how, like, looking inside an atom is easier than looking inside a nucleus, and then looking inside a proton will be more, will need more effort to look inside a nucleus. Proton, what is inside a proton. Now that more energy for us means that we will have to have a more energetic probe or more energetic candidate which will go inside, because you have to cross the nuclear density boundaries. So with the advantage of this accelerators, actually we had beams of electrons which would have extreme energies, so that they can actually pierce inside the proton also. So that is how the things have evolved, and these were the two scientists who actually proposed that when we actually have probes inside the protons and neutrons, we see that these are also not fundamental things. They also have internal structure. There's a famous phenomenon, physics people would know it, that is deep inelastic scattering, which actually pointed towards the internal structure of these protons and neutrons. So what should we, those of course, because protons they carry unit charge, so the internal structure candidate should be actually fractional charges. So that was Gell-Mann and Zweig, which actually proposed that these nucleons, when I say nucleons, it means protons and neutrons, they also have internal structure, and those should be fractional charge particles. Now, naming these particles was actually, there's a rich history of naming these particles in particle physics. This one was actually very funny thing. Okay, there's a novel in which you have this quark word actually occurring in this. So Gell-Mann actually owes this name to the this novel by James Joyce. the word quark. Actually, his first naming was actually K and work, so W-A-R-K, work. But then he was reading this novel, so quarks suited him more, so he gave them the name quarks. So Gell-Mann and this Zweig, they proposed that there should be fractional charge particles within these protons and neutrons, and that they called as the quarks. And of course, nobody believed them at that point of time that this could actually happen, because it was something like shooting a bow in some darkness, and you don't know what is the target. So many people, or most of the people, would not believe them at that point of time, but they assigned these properties to these fractional charges on the basis of the known particles. Like proton is a known particle; it has charge unit 1, and it has to have 3. So this is also a mystery, that why 3? What is the I will talk about it in later on. That this is one of the mysteries, unsolved mysteries till date. That what is holy about the number 3, that we had actually 3 quarks at that. But those people could actually explain the structure of most of the known particles at that point of time in terms of these 3 fractional charged particles. So like you have in the, so we have this up, down, and strange quarks. Later we'll add more to them, and they could explain that proton will be something like 2 these up quarks and 1 down quark, and neutron will be something like this. And if there is a pion, there will be a this quark and an anti-quark. So there's a big theory of this quark model, describing the whole number of particles zoo which is available to us that day. So what I wish to tell our students here, that these fractional charges were proposed, and they could actually account for the existence of the particles in terms of the different combinations of these fractional charges. But then with the evolution of our knowledge in this particle physics, when heavy particles were also discovered, then another generations of quarks were proposed, and they could explain the other heavy things happening. So we have 3 generations of quarks at this point of time, and which are sufficient to understand the particles we know at this point of time. So this first generation, second generation, and third generation quarks. Okay. So let us summarize what have we known. So we have actually started from the basic material, and we know right now at the time we are talking about this phenomenon. We are still here, that we know there is an atom which has constituents as nucleus and electron. Nucleus has constituents as proton and neutron, and then proton and neutron have the constituents as the quarks. So that is our understanding at the present time, that these quarks and electrons are the fundamental things which make this whole, right? So let me summarize. So what is fundamental? So for me, the fundamentals now are the quarks, and leptons means electron, and then there was another generation of leptons, that is mu and tau particles. So these quarks and leptons are the basic constituents, are the fundamental things we know right now. The next thing we should actually know will be that what actually holds them together, so that we understand, we know the world right now. So there come the forces which are which are holding these together. So there are 4 kinds of forces. I will briefly describe them, that which are responsible for holding this together, and then how we have actually progressed on these, and then what are the things which are undone till date, and which pose challenges in our physics. So briefly to recall that these forces, gravitational force is one of the forces which is responsible for our celestial arrangement, and it's actually mass which is the source for this. So we have gravitational force, And then we have this, we had earlier electric and magnetic force, then actually Maxwell gave those famous laws in which these two were unified, and we have this electromagnetic force. We can take questions on that later on if students have. And then there is weak nuclear force, which is the force which is responsible for the decay of the unstable nuclei into stable nuclei. There could be, this is through the emission of electrons or positrons from the exchange of a neutron to proton or a proton to neutron respectively. So we have this weak nuclear force. Then there is strong nuclear force. On the nucleon level, it is the force which keeps actually a nucleus stable, because we have only positive charged and neutral particles there. So electrostatic force would actually make the nucleus burst. So there has to be something which is stronger than this electrostatic repulsive force, which will keep the nuclei together, right? So that was actually Yukawa gave that theory, that there should be exchange of pions, that these protons will be together inside a bag, making a nucleus. And on the quark scale, this is actually the force between the various quarks which are embedded, which are housed in a proton or neutron. So you have to have this force. Then all these forces, they have to be, or every interaction has to be due to certain exchange, and our exchange particle in these forces are what we understand that whenever two things actually interact, they exchange something. So there are exchange particles responsible for all these forces. Maybe we can, there would be questions on this. I would be happy to answer those, but briefly letting the people know that all these forces are due to certain exchange particles, which are mostly bosons, and we understand many of them in a good way, but what we don't understand most of it is the gravitational thing right now. Other forces we know to a very, very good extent. So this gravitational force is by virtue of exchange of gravitons. Then there is weak force and electromagnetic force. There are photons and those bosons. And then gluon is the force which is responsible for the force between various quarks. So then this whole scenario of having fundamental particles, that is leptons and this quarks, and then the exchange forces between two, that is the two forces, and then the force carrier particles like a photon or a boson or this gluon, these all actually make up a certain model which we consider as the certain model, where we understand that the fundamental things, that is the quarks and leptons, and the are those, and they are held together by these forces. So we know the and that model is actually what we refer to as the standard model, and these are its candidates. There are these quarks, there are these leptons, and these are the exchange bosons. We will talk about Higgs a little bit later, okay, which is a new arrival to this. So my part one is over here. So the first question we had asked those questions, that what is the world made of and what holds it together. So those two questions actually stand answered, I suppose, to a good extent, that we have quarks and leptons which make us, and then we have these forces which keep these particles together, and we are as we are right now. So this is the grand recipe we have. We have leptons, quarks, and then we put these forces, and this whole world is cooked like this. But the question is back again, is that really all we know? We have to know, are we know? And the answer is no, it's not. we have not fully understood it till now, because there are certain things which are still, which needs still a lot of explanation. Like we have matter, and we don't, if we say that there are antiparticles and there are antiparticles present, so there is no antimatter, we understand. There is a big problem with the occurrence of the dark matter, which we are not explaining. I'll one by one, I will explain these things. Then we are not sure about how these particles actually acquire mass in the standard model, which is a big thing we don't know. And then if we consider these quarks and leptons fundamental, we have reached up to this on the basis of our energy regimes through which humans have gone. So the question after that will again arise that whether these quarks and leptons, as of now, we understand they are fundamental, but whether they will remain as fundamental is not known to us, because we don't know what is inside a quark. We are constrained by the limit of our energy or limit of our probe, which will actually go inside. Then a big question is that why there are only 3 generations of quarks? How is that happen? And one of the most ununderstood thing till date is the gravity, that we don't know where does the gravity fit into all this, and we know the things. so okay, so we have to have a model actually which would include the explanation to all these, and that will be actually that is right now what we call as the beyond standard model physics. So we have to go beyond the standard model and know all the things, then put these in right place, and we get a new model, and which Einstein said that we will have something which maybe we'll call a super standard model, or revised standard model, or very standard model. Einstein in his later years was actually trying to do the unification of electroweak and the this strong forces, which literature says that he failed until he died actually. So that is how. So talking about the things we don't know is the first one is the antimatter. So if there is a symmetry in the universe, we should actually know the similar amount of antimatter which has happened, but we don't actually we don't observe any antimatter. So there is problems with this antimatter, that where it is, how can we actually produce it, what experiments would actually, this is a big challenge, that like we could produce matter is there. So what experiments could be actually designed to actually detect the antimatter? This is still a mystery. And if antimatter really we could observe, and then what will be the future of physics and as well as the universe actually. Then there is one more mystery, that is of the dark matter. Okay, actually Zwicky observed that there are certain gravitational phenomena happening in the cosmos, okay, which force us to know that there should be some amount of mass which makes this gravitational activity happening. So that, but we don't know what is that mass. That is why it is known to be as the dark matter thing. And one of the biggest challenges in the physics right now is the understanding this dark matter. So I'll be happy to take questions later on. Then there is dark energy, because expanding universe is now a reality and well understood thing. So in spite of the gravitational this pull, in spite of the gravitational attraction, still these things are going, these humongous things are going away from each other. So there has to be some energy which is actually steering all this expansion process. So that expansion process has to be to some kind of energy, but we know, we really don't know what is the source of that energy and where from that comes. That is why that is referred to as the dark energy at this point of time. So we have this statistical thing right now that what we only know is the baryonic matter. That means those protons and neutrons that constitutes only the 4% of this whole universe. Okay, the rest is dark matter and dark energy. So this is two of the mysteries we don't know, three rather. That is antimatter, there is dark matter, and then there is dark energy. Another thing which I earlier mentioned was that what is holy about having these three generations of these particles only? Maybe there could be more, but why only three, and how this is um, mm, going to change if we have antimatter and if we have this dark matter? We don't know. This is a black box right now. Then one of the important things is that people are trying to, as I earlier mentioned, that physics people are reductionists. So we had electric and magnetic fields. So after that, it was electromagnetic thing. Then this Weinberg, Glashow, and Salam, actually, they unified the electromagnetic and weak interaction. So we have electroweak interaction. People are trying to go to the grand unification where strong force will be also, because these forces, as we understand, as physics wise, these R forces should be a reflection of the same thing. It's ultimately something which keeps things together, or which things happening like that. Then so grand unified theory we are still awaiting. And then gravity is something which I said earlier, that this is something which has to be added to this thing, because gravity, we don't know much about gravity. So if there is unification of gravity with these three forces, although we will have theory of everything like that. So, and the third one, the last one is the which I think will interest the students. It was in much news since 2012 when it was actually discovered. That is the Higgs boson, or many people called it as the God particle, because it is the particle which actually is mm, considered to be the candidate which assigns mass to the particles in the standard model. So we have all the mysteries and all the bad news, but there is one good news also, and that is this Higgs boson was discovered on July 4 at the Large Hadron Collider, and Peter Higgs actually got Nobel Prize for this in 2013. Okay, so but this, okay, about this Large Hadron Collider, this is the machine which is where actually most of these collisions are done, where actually most of these nuclear collisions or heavy ion collisions at the energies are done. This is the machinery inside. Okay, this is the beam line in this, but this LHC is to be the experiments are to be done for many things, many other things, like there are experiments trying to see how we identify dark matter. There is people trying to understand the unification of fundamental things. I did not touch the string theory. That is another branch of things which are ununderstood right now. And we have to understand the antimatter and learn about the fundamental forces of this. Okay. So what my I have written it. These are not so concluding remarks, because nothing is concluded. So we know to a good extent what is the world made of. We also know to a good extent what holds it together. But what we really don't know is how good this good extent is. So, in spite of knowing all these things from within the microscopic world of nucleus or proton up to the this celestial universe, okay, we know many things, but we are yet to know uh, much more about these. So we have to have so the people who are our students I think it will be helpful to them to see that what are the challenges in the physics. But then there is a need of experimental facilities, okay, because those only could actually explore that how deep we have actually dug and how deep we still can know. So till then, I would say that we have to suffice with our what we think in our heads, and that's all I have to say. Thank you very much for your attention. I will be happy to take your questions.
Dr. Kutsia, are you moderating this Q&A session?
Hello, good afternoon, sir. Dr. Wasim Saab.
Yes, please.
Are you fine, sir?
Yeah, alhamdulillah, fine.
Thank you, sir, for such a nice talk, for such a nice lecture. Because these being the basic things which are initially required by our students to get their concepts clear.
Yeah.
Thank you so much, sir.
Thank you.
In fact, I agree with you, sir, that scientists' greater pleasure comes from the theories that derive the solution to some deep puzzle from a small set of simple principles in a surprising way.
Right.
I would like to add that we can imagine the extent of excitation of a student or a research scholar or a scientist who assembles a transistor from the given components, and when he switches it on and listens to the first sound, really it is very much exciting. Whether it is the case of the study of the black holes, pulsars, or even lasers, it is not less exciting.
That is true.
I agree with you, sir, that it is the human nature which is very curious to know about the things. Now, here I would like to ask you, sir, that we are talking about the physics as a study of the laws of nature and the application to the non-living things. Right. Now, does it mean that doing physics is something solving the problems with riddles with which nature confronts us? Or can I say like that physics is what physicists do? Is it much like learning to play a game?
No. Dr. Saab, okay. Are you done with question?
Yeah.
Okay.
Thank you, sir.
I think it is not like that. Okay. You see, physics is not done as the physicists do. Every science is done on the basis of there. I have said that people are curious about it. Then there is another curiosity. I said where actually we do the things. Okay. I should have actually added the third kind of thing, which is which is the case of the invention of wheel. Okay, it is the convenience. We as humans actually wish to make our life convenient. We like you talked about the transistor. Okay.
Yeah.
So earlier we had in our house there was radio also, there was watch, there's watch also, there are many things, but now we have everything in our pocket in the mobile. So it's because of we science is something which we do to make our lives comfortable also. Okay, so it's not only as we do science, like if we do physics, we are doing this imaging of this people. There's a big physics involved, and that is how diagnostic things are
Yes.
okay.
Yes.
So there are certain things which have come into science or physics in particular accidentally. That is true.
Yes, that is true.
They have accidentally evolved, and the things were.
But it has been the
Like
curiosity of a man.
Yeah, radioactivity was that was an accidental discovery. Okay.
Yes.
then the point of a good scientist is that you have to harness it in the positive manner. Okay,
Right.
radioactivity was an accident, but then if you see its applications right now, okay, it is the biggest gift of the science to the human being, where you actually right now you are treating the, like you talked about this laser and these things, how many diseases are being treated by this, how much diagnostics is being done by this. Okay, so every small discovery actually has a bigger impact. Okay, but then there is as humans, there we are interested, we are like, if I'm doing a good thing for the sake of a reward also, that is one kind of psyche we have. We are doing certain things for the sake of my comfort. That is another kind of psyche. And then there are gifts from nature, so those are accidents, good accidents, which give us good things. Okay, is that okay?
Yeah. Thank you so much. I think.
Sir, I have a question. Though I'm a
Yeah,
person
sure.
from computer sciences background,
Right, okay.
uh, this is more of a general question because I suppose this was not a hardcore physics talk.
Yeah, this was definitely not
This
as
was
it
more more general about sciences.
right.
You know, as you said, science is about curiosity, and more curious behavior means more innovation in sciences.
Right.
I have a question which is related with how students perceive science, particularly physics, because there's one part of science which is for the commons. For example, let's take an example of COVID vaccine. Everybody, a common man, would connect with it. Okay, this is kind of a science which is very beneficial to me. So as a student, I can go into this kind of a science because it opens up a whole new range of possibilities for me,
Yeah.
as well as for the humanity.
Mhm.
Then there's another kind of science, like there's a Mars rover on the Mars. How beneficial is it? It is right now for a common person. Yes, it is futuristic. It is something which will do good for the humanity in a larger context.
Mhm.
So, is there a need to revamp the entire education system and connect the scientific advances that we intend to do in the future with the curriculum, so that as a student I can see some interest in physics? If I confine it to physics, I can see some interest, because मतलब मुझे क्या लग रहा है physics में there are more of a lot of things are accidental discoveries and inventions. So
Mhm.
people say, okay, what is the contribution? Somebody observed something, he had the knowledge, background knowledge, and he then tried to rationalize it and put it in the perspective.
Right.
So, as a student, is there a motivation for me to really take up some specific kind of a science, so that yes, it caters to my the career, and then it does good for the the other part. अगर मैं computer science की example ले लूँ कि we talk of artificial intelligence, machine learning, quantum computing, but those are the things which we actually implement. We do. This is not confined to theoretical or theories only.
Mhm.
And as you said, you are a reductionist. Study the item and then go to the cluster. The cosmos is the
Right.
ultimate
True.
thing.
True.
So from a physics, because I've studied physics at a graduation level, but somehow I lost interest after my graduation. Assuming that it's not something that, yes, it's a life touching thing at the moment. So
Okay.
from that perspective, I'd like to listen your take on that.
Okay. Sure. See, one thing, your question has to be, I think, you have to correct me,
Uh,
that people like our students right now, okay, most of us teachers, many of us, so we actually, for us, I'm saying, then I will give you the answer to your question is different. Okay, we study whatever we study for the sake of career.
Fine.
That is where the role of actually teachers comes. Okay, so we have to, if there is any of the student here, I have always tried to tell the people that physics is not the whole world. Like doing physics will not, you will get 90% and then you will do a PhD. It's not the whole thing. Before that, you have to have something which will give you the satisfaction that you did something, and that is what is your question, I suppose. Like if you have if we reach to the Mars, what to me, how does it matter to me? Okay. Now the point is that see, you have to take the human angle in this also. Okay, you cannot actually see everybody thinking like that. We cannot do that. We are actually, I think this question is there because we are looking at this scenario which is around us. There are people like, there is a simple technician at CERN who actually is responsible for just maintaining the machinery. But when it is said that a Higgs boson is actually discovered, okay, he is part of that celebration. So in addition to having a career, that means which will bring us the comforts, okay, there has to be some kind of thing which the human psyche which has to be touched by the human psyche. Okay, now there's no answer still to your question. That comes now. What, and it is my take on it. Okay, and people can have different views on this. Okay, I understand that whether you take the basic human psyche or whether you take the general things people think of, science is always cherishable. It's always cherishable. If somebody is taking physics, for example, as a career, okay, we see many things which have been very small, significant in earlier, like we are doing, for example, material science. People are doing material science. If you see, they do a small change in a certain compound like zinc oxide. Okay, they do a modification, structural modification, which is insignificant, but that brings a significant change in the application of that material. So even if he is doing some very insignificant thing, okay, many people are telling them, "Oh, changing a small structure and you publish a paper," but that is not true. That small change actually makes some material useful in a bigger way. Okay, like we have this transistor evolution. You are doing computer science, you might know how transistors have evolved from um, that earlier, what were those called, and to the
Vacuum
present
tube.
day, vacuum tube, those to the present day things. When I remember when we bought the first computer in our lab sometime back in 88, it had 128 GB basic this hard disk drive. Okay, now you have how many GBs in your mobile also. So this has drastically changed us. Same is the case with physics. If knowing that galaxies are expanding, this universe is expanding, doesn't mean that it does not matter to me. It definitely matters. If I can actually put a small contribution it definitely would matter. And it is okay. That is in a lighter mode from me. That it will earn the person who is doing physics bread, at least, right? So I suppose that is, maybe it is not what you wish to know, but that is how I think on these lines.
Thank you. I think let's take some questions from students.
Yeah, sure.
Yeah, exactly. Respected faculty can ask some questions if they are interested. I think the concepts are very basic. Everybody knows these, and the explanations to some extent. Our students may also be knowing some facts.
Yeah.
So there are hardly some questions. If respected faculty has some doubt, they can ask some certain questions.
Students should ask questions. There are no
They are waiting for their sponsor.
Do we have any questions in the chat box?
No, we don't have any question. There is no question.
Sir, I have a question.
Yeah, sure, please.
Yes. Sir, without mathematics, can the student which has no interest in mathematics, can he go for physics for inventions?
Ideally, I would say no, because mathematics is language of physics. Okay.
Yes.
So if you don't know the language, how can one actually do the things? Okay.
Right.
So
Invention part without mathematics.
so invention, like for example, if somebody has to invent, for example, if wheel was not invented, if somebody has to invent it right now, okay, mathematics would tell that what would a toy, how much diameter or radius a toy will need to move on, and how much a big van would try to move. So mathematics cannot be actually taken out. Okay, if we are taking out mathematics from sciences, physics is just the body. There's no soul in it.
Yes.
So it can actually be a live body. It can be a live person only if it is soul and body. So that is mathematics and physics. Without that, we cannot do. I think that is the non-separable things. These two things.
Yes. That means this is the answer to Rashid Sabu's question also, that people lose interest in physics because they have not good hold of mathematics.
Yeah, that is individual cases. Those are individual
Yes.
cases, definitely. And people who are afraid of mathematics actually.
Yes.
Don't
They lose interest in physics also.
They lose interest in physics.
Yes.
There is a point that
Sir,
I want to add here.
there is a question, Aisha Manzoor from
Okay.
Aisha Manzoor. Sir, what is the concept of string theory?
Yeah, okay. String theory is okay. I did not touch it here, but
Yeah, sure. You did not touch it, but she is curious to know.
I will say. You see, when I have said, for example, okay, I will answer you. Right.
Sure, sir. Please continue.
Okay. When I said this interaction thing happening between two things. Okay, if these protons actually they are positive particles, they are inside a bag in the nucleus. Ideally, they should actually burst because they are same charged particles, and they will repel each other, and it will go. Now, one theory is that we consider that there is a strong force, then they exchange a ion between them, so they remain stuck together. String theory actually says that every interaction which is happening, like here I am considering that a particle is being exchanged between two particles. String theory tells us that every interaction actually is something which is like two particles which are interacting are connected by a string. Okay, I can have a visual also. I suppose I have it here. Just I just give me a second. I'll get this visual about string theory. String theory. Okay, so now I have to share it. I can't find it, but okay, let me. So string theory tells me that this exchange is not like between two particles. The interaction is because these two particles are connected with a certain kind of, just like a rope, and that rope is the interaction. So that is another, that is the theory which explains the interaction between two particles on the basis of one unseen kind of string between two particles. So that whenever this interaction takes place, like those two particles are attracting or repelling, it is actually the contraction or the repulsion, this what you call as expansion of that string. Okay, so string theory is about that. Again, there are string theory is still you will not find in many books right now. Many people not actually doing string theory because this theory of exchange of particles is more answering many of the things right now. But string theory, it's not the particle which is being exchanged, but it is everything which is sharing something, or every two things which are interacting are actually having an unseen kind of string between those two particles. That is string theory. Not the, I'm telling you the conceptual thing, not the exact theory of that. Okay, instead of exchanging the particle between two, they are connected by unseen strings between them, and which are responsible for attraction or repulsion of those particles based upon that. Then they have dimensions of those strings, that when it contracts or when it actually expands, depending upon the particles go from each other, far from each other, or they interact. That is how string theory. I was having some visual, but anyway, I'm not able to find it.
Can I? There is another question by Aisha.
Please.
Yeah. What will happen to the forces between the particles?
Okay, I can see the questions.
Yeah.
What will happen to the forces between particles?
Between the particles.
What is the question in that?
Earlier it is.
No,
then we can.
Where is antimatter
This
found?
is the second part of their question. Aisha has first put what is the concept of the string theory. Then she has put the second part of it. What will happen to the forces between the particles?
I got it. So the same thing happens. Okay, string theory does not actually differ from the end result of the interaction between two particles. Okay, whatever our theory of exchange particles says, that if they are two, for example, there are two mass particles, exchange particle theory tells us that they will always be attracting each other by virtue of gravitational force, because mass is there. Then if they are charged particles, there will be exchange of photon, and these will attract or repel. Okay, so when we say that they will attract, this string will actually have contraction. Then they will actually repel. The string will actually get expanded. Okay, so that is how these are two parallel concepts of interaction between two particles. But yes, string theory does not have an experimental support as of now. That these strings really, they could have been having phenomenological support, that is the support due to the mathematics of the interaction between two particles. But experimental support is with the exchange of particles between two particles, exchange of a new particle between two things, which will make it to attract or repel. I think that was the question. Huh?
Yeah, sure. Sir, one more question from one more student.
Yes.
Sir, where antimatter is found?
No, that is what I said. Antimatter, we don't know where is antimatter. So that is one of the unsolved mysteries I enlisted, that we don't know where is the antimatter. So that was here. So we don't know where is the antimatter, but it has to be there, because most of the people believe that when universe actually, even if you believe the Big Bang theory, okay, it was a symmetric thing which was produced. Okay, so there was matter as well as antimatter, but we see the matter, we don't know about the antimatter. So antimatter is still missing.
So I think there is no more question. Some students are trying to write, but it is not visible. I think
give them some more time.
Madam Samina, there is no more question from students.
I think we can give them some more time if they are trying to write it still.
Yeah.
Let us wait for a minute or a while.
Okay.
So by the time the students start writing more questions,
Yeah,
I want to add
yeah.
some points that were discussed before, particularly in response to what has been asked about the kind of developing interest in physics. See, an important point that I would like to add on my part here is that in addition to mathematics, in physics, we do research and we find solutions to problems on the basis of modeling. We do a proper modeling of the problems. It is because we are able to imagine a problem, design a problem, model it well. That is why we are able to find solutions. That's why we have been on Mars or we have been able to probe cosmos, because we are able to deal in terms of and think in terms of proper models. Those models are based on those theories that we hold irrelevant, because theories are not irrelevant. Theories are based on certain conceptual ideas, on certain logical reasons. So once the theory appears to be sound, on the basis of that theory, we develop a model. And on the basis of that model, we try to find solution to a particular problem. And because we have well-defined problems, that well-defined models that suit every problem, we are able to find solutions. That's why we have been able to do big things like landing on Mars or probing the cosmos. And in biological sciences, because we were talking about COVID-19 perspective in some question before, because COVID-19 is basically the problem of chemists and biologists, although it's also the problem of physicists, but it doesn't purely deal with physics actually. Because COVID-19 is basically a problem that pertains the science of biologists. And in biology, we don't do any research on the basis of modeling. It is done in a very random manner. Remember, biologists pursue their research on the basis of hit and trial methods. And in case of hit and trial methods, you need to be lucky. As long as you are lucky, you are able to find the solution of the problem in time. So that's what completes the answer of that question, I think.
Wow. There is one more question from Jamila Ashraf. She wants us to know that if a student is weak in quantum physics, though good in other branches, then what would you like, sir, to suggest for that?
Oh, yeah. Okay. Okay. This is a good question. You see, quantum physics is not the whole physics. Okay. This is one branch of physics. Okay. You can leave quantum physics back and go beyond this and do something where you will not do quantum physics at all. Okay. So, but of course, our educational system at this point of time means that if you have to earn a degree, you will have to pass the quantum physics paper also. Okay. So that is a very, very honest answer to that. Okay. But failing the quantum physics paper, you will never get an MSc physics certificate. So that is because this is one of the basic. There are certain basic courses in physics, okay, which are needed to do. For example, you cannot do away with the mathematical physics and say that you will do any kind of research after that. But okay, there are things where quantum physics you will not use in your further studies. You can do,
but it is a requirement.
But for our educational student, you have to at least pass this paper in the MSc course. Okay, you cannot say that I am not good, I will get 100 out of 100 in other papers, but let me get an MSc degree without passing quantum physics. Okay, that cannot be done. That is not allowed in our present scenario of education. If we go in future, if we actually get an MSc degree on a single subject, that okay, I know only thermodynamics and I can only do thermodynamics, so let me do it and do an MSc on that, then you will be lucky at that point of time. But as of now, you have to but yes, of course, after doing your physics, you can do many things where quantum physics will not be required to that extent. Okay, you can do the world is all yours after that, but the requirement is like that.
That means that if she is not good in quantum physics, she can choose other branches of physics. And with the passage of the time, she can go also for quantum physics once she qualifies her PG.
There is exciting range of experimental physics which is being done. Okay, like just simply making a detector. You don't need a quantum physics there. Of course, you need certain things, certain parameters, but you don't need to solve those 20-page those equations and then say, oh, it is good physics. That is not only physics we do. Okay, even just connecting a wire of 10 micron with a plate is also physics. Okay, people can do that. That is considered to be good physics. And there are Nobel prizes being done, like the Nobel Charpak, who actually discovered this gas detector. So he got a Nobel Prize for just making a wire detector, a wire and enclosed by a cylinder. Okay, so that is all he made. And he said when a charged particle goes, it will lose energy, wire will get a deposition, and you will get a signal. That's all he did. Okay, and that earned him a Nobel Prize. Okay, so this is again a syndrome with okay, I'm sorry, it's not insult or humiliation to anybody. This is a syndrome in Kashmir particularly, that doing theoretical physics to a large extent and solving those big equations is the physics which it means. That is one part of physics we do. Okay, there would be somebody who would actually not remember the Schrodinger equation, for example, but he would be a good physicist. He will do a good amount of significant physics, even just forgetting about who Mr. Schrodinger was. Forget about Schrodinger, and he can do significant physics and earn a good amount of things from that.
I may tell you, sir, she is satisfied with your answer to her question. That means she is not interested in quantum physics. She will go to nuclear part, nuclear portion of it.
I said the whole world is yours.
Yes, exactly. I think there is no more question. Dr. Kutsia may proceed further.
Okay, for vote of thanks.
Yeah.
Is that needed?
Okay.
Yeah, but we are waiting for their questions. Nobody is asking.
So
yeah. One minute.
Fine.
There is one more question. Is dark matter present everywhere?
Okay, so let me answer this. So
we will move to dark matter and dark energy.
Yeah, dark matter. So see. So this inner, see, why do we say there is a dark matter? As I said earlier, that there are things happening in the cosmos, okay, like big galaxies moving from one place to another place, okay. So there has to be something, because this all is based upon the present knowledge of our forces. What forces do we know right now? We know there are forces between two charges. We know there are forces between two masses. And we know there are forces between those quarks, between inside a nucleus. So if some activity is happening, for example, okay, for the student, I will give an example regarding the black holes. How do we say that there is a black hole? So how do these cosmologists do that? So they observe something which is going around and round and round, and we don't know why. It cannot be without having a particular force which is keeping it going on a particular thing. There has to be something in the center which will provide it the necessary centripetal force to go around and round. And that is how black holes are predicted, that there is a black hole. Similarly, if we are seeing the present cosmos, which we know is having some activities going on, they have to be because of the influence or effect of certain huge mass, which will make it go like this, okay? And that is why we say that there is kind of a matter which is actually responsible for this whole activity. So we are actually engulfed by this whole dark matter. So this is all around us, and we are a small thing at the center of this dark matter. So statistically saying, you can say dark matter is everywhere. Statistically, you can say dark matter is everywhere. Okay.
Yeah. Thank you, sir. This was really a very good question, and it was put forward by our student Insha Nisar Bhatt.
Good, very good. Very nice. Is she okay with the answer?
Yeah. She is okay. Now, Dr. Kutsia, please go ahead.
Okay, fine. So, Assalamu alaikum, a very warm good afternoon. On behalf of the principal of the host college, faculty members of the Department of Physics, And the students of the non-medical stream in particular, I thank the speaker, Dr. Wasim Bari, Associate Professor, Department of Physics, University of Kashmir. Sir, it was indeed a very wonderful session. You have kept the attention and the interest of the students captivated throughout. The session was very lively, very interactive. The students have posed very relevant questions, true to their level of understanding at this level. So I think that is what essentially serves the purpose of these webinars and seminars, that at the end of the day, we are able to inculcate in the students a sense of motivation towards learning physics and tell them what kind of different career-making opportunities and prospects is awaiting them after having chosen physics as the discipline. So we thank you once more that despite all your official commitments and the fact that your parents are not keeping a good health, you have taken out time for our students. Thanks are also due to the members of the college IQAC committee who have indeed put very tireless efforts in making this entire webinar series a successful venture. And today's event marks the end of the series. At the end, I want to thank our worthy principal for her wholehearted support and cooperation in organizing these kinds of events in the better interest of students. I would also like to thank the convener of the college IQAC committee, Professor Rashid Malik, who has also taken very keen interest in the management of this entire affair throughout the course of this month. That's all.
Thank you.
Thank you, sir.
Thank you very much.
Thank you, sir.